Mounting a multi-ton star above Barcelona in 2026 is not merely an architectural milestone, but the absolute culmination of a structural stress test for a system engineered over a century ago. The entire basilica functions today as a massive, active testing ground for extreme environmental and gravitational loads. A colossal crawler crane slowly lifts the 12-pointed glass and steel luminary into the high altitude. The metallic tension of heavy steel cables vibrates audibly in the coastal air as they manage the immense vertical strain. The payload weighs 5.5 tons, carrying the mass of heavy construction equipment, yet it must balance perfectly atop a strikingly narrow stone spire. Engineers lower the module onto a custom stainless steel pyramidal core, where high-strength anchor bolts immediately lock the complex geometry in place. The fixation is absolute. This direct mechanical integration transfers severe wind shear and static weight straight down into the central masonry shaft without fracturing the stone. This precise maneuver finalizes a formidable timeline that initially commenced in 1882. A devastating civil war that incinerated the primary structural blueprints, two global conflicts, and a modern pandemic acted strictly as mechanical delays rather than project cancellations. The fundamental engineering survived. A wide aerial shot ultimately captures the completed tower anchoring the urban skyline, finalizing a continuous construction cycle of exactly 144 years. Massive vertical loads demand extreme solutions. To withstand colossal pressure for 144 years, engineers abandoned traditional Gothic physics. Classic cathedrals rely on thick walls. Heavy flying buttresses push back. Gaudi chose a different path. He removed outer support systems. The inner columns act like trees. Solid stone twists upward. Trunks split into branching limbs. Vectors shift. Tension drops. This internal forest holds skyscraper weight. No external crutches exist. 18 separate towers unify the grid. Weight transfers seamlessly. The structure balances perfectly. The highest spire targets the sky, but limits exist. Topography wins. To respect the natural elevation of Montjuic Hill, the central tower halts at exactly 172 meters, securing a precise 1-meter gap below the mountain peak. Calculating the thrust vectors for these complex tree-like columns required zero digital processing. The entire load distribution algorithm lived inside physical databases that were almost erased forever in 1936. The structural paradigm shifted in 1883, when a standard parish project transferred to Antoni Gaudí. He immediately discarded flat blueprints. To compute extreme structural forces, Gaudi built inverted scale models using hanging chains and lead weights. Gravity pulled the chains into perfect catenary arches. This mapped the load lines naturally. He then translated these precise tension curves into complex three-dimensional plaster matrices. The underground workshop functioned like a massive analog computer. By the time Gaudi died in 1926, crews had finished less than 25% of the structure. Then history intervened. Today's laser-guided assembly operations stem from a single catastrophic rupture. Jump back to 1936. Militants breached the basilica crypt. The sharp crunch of shattering plaster matrices echoes through the dark laboratory. Flames consume the original architectural blueprints. Decades of structural mathematics vanish overnight. The master code is gone. Modern construction acts as a pure forensic engineering operation. Structural engineers must reverse engineer Gaudi's original logic by scanning the surviving geometry of those smashed models. Shards of white plaster lie scattered across the stone floor, waiting for decryption. Reconstructed models revealed the harsh truth. The Tower of Jesus Christ requires extreme rock density. Original Montjuic sandstone reserves are dead. The mountain is barren. Target height demands absolute structural perfection, 172.5 meters. Engineers hunt for global substitutes. Rock must handle colossal compression. Diamond wire slices the quarry wall. Heavy stone blocks tear free. Dust plumes rise. The natural texture feels incredibly rough. Raw stone enters the laboratory. Hydraulic presses crush the samples. Pressure hits hundreds of tons. The dense surface holds firm. Zero microcracks. It survives. Weight dictates everything. The summit demands a crowning cross. 17 solid meters of stone, equal to a 5-story building. Glass and ceramics coat the surface. Sunlight strikes it. Base integration begins. Testing never stops. Technicians prepare super heavy stone modules for immediate dispatch to the active construction site, building immense structural tension right before the final vertical lift. To realize the construction of 170-meter towers, solid rock must take on mathematically impossible forms. Columns change their cross-section right in the process of growing. At the base, a massive pillar begins as a strict hexagon. As it rises upward, the geometry morphs, twisting fluidly into an octagon. Near the vault, the stone fractures into multiple branches, mimicking a colossal tree trunk splitting into thick, load-bearing limbs. It is a structural paradox. Straight lines do not exist here. Extracting the raw material is merely a brief prelude. Massive raw blocks weighing tens of tons, roughly the weight of 2 fully loaded city buses, arrive at the fabrication workshop to undergo a radical metamorphosis. Here, the digital process takes absolute control. Engineers feed intricate 3-dimensional model data directly into 5-axis automated milling stations. The transformation begins. A diamond-tipped cutter, spinning at 10,000 revolutions per minute, bites into the dense rock. It carves the complex, twisting curve straight out of the solid mass. Coolant hisses against the friction-heated stone. What would demand weeks of relentless manual chiseling from traditional masons now happens in just a few hours. Yet, automated precision cannot finish the job alone. Technicians step in to refine the organic curves by hand, meticulously grinding away microscopic millimeter-scale deviations. Under their abrasive pads, the raw rock changes state. The final surface emerges completely smooth, cold, and flawlessly polished to the touch. The cycle repeats without a single pause. Across the active shop floor, industrial milling heads plunge back into heavy stone blocks, aggressively carving out endless twisting surfaces for the canopy. Natural stone easily supports the immense crushing weight of heavy vertical columns. But perfect geometry is useless if, at a height of hundreds of meters, natural stone crumbles under the continuous pressure of horizontal winds. Under intense lateral bending from seismic activity, rigid rock completely lacks flexibility and fractures like brittle chalk. At an altitude of 170 meters, continuous atmospheric gusts exceed 100 kilometers per hour, generating relentless horizontal vibrations across the exterior. To survive these environmental forces, the structural design requires a completely concealed internal framework. Engineers integrate a complex network of high-strength steel cables directly into the core of the newly carved panels. This internal skeleton specifically absorbs the violent tensile stress that would otherwise tear the rigid masonry apart. The hidden material combination creates a profound engineering paradox. A visually traditional stone cathedral actually possesses the exact load-bearing capacity and kinetic flexibility of a modern steel skyscraper. As hydraulic jacks pull the vertical steel cables tight, the fundamental mechanical properties of the tower radically change. The external stone provides unyielding compressive resistance, while the inner steel spine bends without breaking under dynamic atmospheric loads. The tension holds. The extreme mechanical pressure physically locks the individual carved blocks together into a single monolithic mass. Engineers abandon traditional layer-by-layer masonry. They move assembly into workshops. This integrates the steel network. Precision becomes absolute. Diamond wire saws cut rock. Blades scream. Cold water blasts the stone. Workers carve exactly 16 blocks. They assemble the curved geometry. Engineers integrate hidden steel nodes. Hydraulic jacks pull the cables. Steel tendons groan inside rock. Friction locks the entire mass. Modules come alive. They stand completely structurally independent. They bear their own loads. One panel outweighs a bus. Forces transfer directly downward. Routine inspection begins immediately. Lasers scan the physical dimensions. Inspectors demand perfection. They verify tight structural fits. The math speaks. 16 solid blocks per module. 8 structural panels interlock perfectly. They enclose one complete level. By shifting the extreme structural hazard from the open sky directly to the controlled factory floor, the overall assembly speed increases exactly 16 times. When a structural module weighing between 7 and 10 tons leaves the factory floor, it faces its absolute final test. It must dock at a height of dozens of meters. The allowable margin is exactly 1 millimeter. How do you perfectly align microscopic bolt holes when a colossal stone block sways in the wind? Specialized tower cranes hoist the heavy panels into the open sky. At these altitudes, aerodynamics dictate the rules. A sudden gust turns the module into a dangerous pendulum. You can feel the sharp micro oscillations vibrating right through the steel tension cables. Installation halts completely if wind speeds rise above the safe limit. One rogue swing ruins everything. The extreme contrast defines the danger. 10 tons of solid mass must slip into a target zone no wider than a credit card. The crane operator and the ground crew execute a slow, controlled choreography of hand signals to guide the descent. If the geometry misaligns by even a fraction, workers manually muscle the massive component back into perfect position. The final steel bolts slide in. Heavy wrenches lock the joints. Movement stops completely. The panel merges permanently with the tower. The massive load shifts silently downward. The upper steel framework liberates the interior space of the basilica, immediately demanding the stabilization of colossal vertical loads. Traditional Gothic architecture relied on exterior flying buttresses to prevent massive stone walls from collapsing outward under the immense weight of the roof. Here, the engineering logic completely eliminates external supports, forcing the kinetic energy of the heavy central towers to travel strictly downward. Zero outward deflection. A precise structural network of 56 internal columns accepts this monumental gravitational challenge. The architectural mechanism operates as a continuous descending sequence of converging vertical forces. The crushing weight of the upper tower presses directly into the angled branching nodes near the ceiling. From these upper intersections, the mechanical stress travels down the diagonal extensions, gradually merging into the thickest part of the central pillar. The concentrated mass then drives straight through the solid shaft and anchors deep into the bedrock. Ordinary limestone would instantly shatter under this extreme pressure. The central structural supports, therefore, consist exclusively of red porphyry sourced directly from volcanic deposits in Iran. This igneous rock forms a tightly locked crystalline matrix during rapid cooling, resulting in ultra-high density and an absolute monolithic structure. The unyielding, cold stone surface viciously resists any mechanical impact. Structural failure is impossible. The specific material properties of this volcanic rock provide an astonishing compressive strength exceeding 200 megapascals. Such geological resilience translates into pure mathematical endurance. One central porphyry column absorbs a direct downward load of 6,000 tons, a mass equivalent to a heavy freight train resting on a single structural point, beyond 56 load-bearing columns. Mass reduction demands new shapes. Window geometry radically changes. Not just art, aesthetics hide pure mathematics. Forget classic thick Gothic walls. Openings use hyperbolic forms. Stress shifts downward. Parabolic curves redirect the weight. Massive stone structures shrink. Walls grow thinner. The structural load drops. Light waves hit complex angles. The eastern facade filters blue-green. Morning photons pierce the glass. Colors ignite. The western side shifts red-orange. Mathematical grids catch the sun. Geometry bends light. Vibrant spectrums of solar radiation continuously refract through the precisely calculated structural panels across the shifting interior surfaces. Realizing the complex parabolic shapes of the stained glass systems and calculating the crushing loads on porphyry columns required the complete integration of 21st century technology. Construction spans more than 100 years. A radical chronological shift defines the entire process. In the late 19th century, bare hands shaped wet plaster. Craftsmen painstakingly sculpted delicate geometric models. Today, those physical fragments transition directly onto illuminated monitors. Advanced aeronautical design software renders the exact structural stresses in real time. The technological leap is absolute. Porphyry is an exceptionally dense volcanic rock. Shaping it manually previously consumed months of grueling labor. Now, a high-speed robotic milling arm engages. The piercing mechanical whine of a diamond-tipped cutter tears through the heavy stone. Pressurized cooling water sprays across the friction zone. CNC robots carve the intricate hyperbolic blocks with absolute millimeter precision. Engineers construct a massive stone cathedral with the microscopic tolerances of a mechanical watch. Every structural component arrives at the assembly zone perfectly calibrated. No manual adjustments, zero structural deviations. The century-long roar of heavy construction machinery steadily approaches its final echo. When the last carved block locks into the towering structure, the massive diesel cranes will detach. The intricate grid of steel scaffolding will completely dismantle. The protective barriers will fall away, leaving an entirely empty stone courtyard courtyard beneath the monumental facades. Software models timelines. CNC machines lock schedules. Engineers approve the dates. 18 towers get deadlines. Target 1 arrives. Crews hit February 20th, 2026. A 17-meter cross rises. The Christ Tower tops out. Altitude breaks records. Sensors record 172.5 meters. That equals 50 floors. Earth gets its tallest church. Next phase begins. Schedules demand 2033. The skeleton stands complete. Heavy cranes leave. Sculptors take over. Only decor remains. Yet after 150 years of construction, the ability of this massive complex to withstand urban vibrations remains the ultimate unknown for 2035.